Okay, now let's go to electric generator. An electric generator is a device that converts mechanical energy into electrical energy. Let's pay attention to these two types, DC and AC generators. For DC, we call that the dynamo, so this example. In this case, we have a disk that's rotating inside of a constant magnetic field. When that happened, because this is a conductor, right, we have, imagine it's rotating in this direction, and imagine that the magnetic field, where the magnetic field is going into the wall. So we have the magnetic field into the wall, we have the velocity, so we have a force going down. Remember, we use the right hand rule. This is the magnetic field, this is the velocity, the force is perpendicular to this plane. Okay, perfect. In this case, the charges are moving toward this edge. So the charges are moving toward this edge, so this becomes, let's say, positive, then right here becomes negative. So we are separating charges, so we're creating a potential difference. When we join these 2 points, this point and this point, we create some current through a wire. Okay, this is the dynamo. What about the alternator? The alternator is a set of coils, right, rotating inside of a magnetic field. When that happens, a current is created. But now this current goes up and down, or is oscillating, right? That's why it's alternating. The symbol for this is as a wave, right? This is the symbol for a AC generator. For a DC generator, the best example is the battery. And the battery has a symbol, right, in this way. It's negative, positive. So this is the battery, and this is the generator. Produces a wave, right? The particles, the electrons, right, oscillate back and forth, back and forth. Right here, the current is direct. It goes from one point to another point. That happens in the battery. Okay, now let's go to the case when we have the alternator. And we know that the magnetic flux is found or defined as the magnetic field times the area, in this case of the coil, times cosine of the angle. But the angle can be also defined as omega t. Right, and also from the Faraday's law, the electromotive force is equals to negative the number of turns or loops times the change of this magnetic flux with respect to time. When we do that, we can see that only the angle is changing. The angle of the area, this is the direction of the area this instant, and this is the direction of the magnetic field, right? And we have the angle theta, but because this area is rotating, so the angle is changing. The area is the same, magnetic field is constant, the number of terms is the same, so we're changing only the angle. But the change in the angle, cosine omega t respect to time, we can use now some calculus to make it faster. This is the same as saying the derivative of cosine is just negative omega sine omega t. Let's take that for granted, and let's plug this value right here. And what do we have? Then the electromotive force, let me draw it right here. The electromotive force is equals to NVA omega sine omega t. Or we can represent this in this way also. This is the electromotive force is equals to a constant. This is going to be the amplitude because it's going to be a wave, right? Because of this sign produces this function. So this is going to be the amplitude. The amplitude is going to be epsilon naught, which is this one times sine omega t. Well, epsilon naught is this quantity, right? It's going to be epsilon naught is equals to NVA omega, correct? Okay, perfect. Now, Again, this is voltage or EMF for a alternator. Okay, perfect. Now let's go to the inductance. Inductance, great. When we have a coil, right? When we have a coil or a solenoid, right? Like in this case, in a circuit. Imagine this is a circuit right here. For simplicity, let's use the battery for simplicity. Okay, we have an open switch right here, and then we have the inductor. This is the inductor, just a coil, wire in a coil, correct? And imagine we have right here a resistor. Okay, now when we close the circuit, this is the batteries have voltage. We can use voltage or we can use electromotive force. Okay, the function is the same. Okay, now let's close the switch and what happens? Well, at the beginning there is no current, but later we have current. But as long as we have current inside or going through this inductor or solenoid, right, we have the creation of a magnetic field. So the magnetic field created by this coil opposes or create a current that goes in the opposite direction as the original current. Remember, we explained that in the previous video. We have a magnetic field. We have this is a magnet. This is south. This is north. Right, it goes down, and we have a coil. Right here, we have coils. When the magnetic fields interact with this coil, a current is created. But this current also creates a magnetic field, right? A magnetic field, right, that opposes the incoming magnetic field. Right? That is happening right here. The same thing, we have coils, so we have the creation of current, but current produces a magnetic field, and the current again is gonna be in the direction opposite to the incoming current, right? The induced current. This is also called the back EMF, right? Back EMF. That happens only when we have a change. Every time we have a change right here in a solenoid or in the inductor, we have a back EMF. But later, right, the current is gonna be constant because this is the battery. The battery creates a constant current. Only happen in a fraction of time when we create this back EMF. Okay, perfect. Now, one more time. This back EMF, right, the electromotive force, is equals to, actually it's proportional, right? It's proportional to the change of the magnetic flux respect to time, right? The change of the magnetic flux respect to time. Okay, but what is happening also, that let's pay attention now in the current. Again, the current is opposite. In this case also, this is proportional to the change in the current respect to time. Correct? The change in the current respect to time. How do we eliminate this symbol? Using a constant. So that constant is called the self-inductance or just inductance. It's gonna be the electromotive force, right? It's the back EMF produced because of this situation right here is equals to this constant, which is the inductance or self-inductance times the change in the current respect to time. Right? So we have then this electromotive force produced by this inductor. Okay, the inductance change in current respect to time. Perfect. Now let's go back to the Faraday's law. This is from the previous chapter, right? Faraday's law tell us that the electromotive force is equals to to negative n, it's not right here, let me write it right here because this is very important, is equals to negative n changing the magnetic flux with respect to time. Okay, let's do it right here. Maybe changing the magnetic flux with respect to time. Okay, perfect. Now, also it's found that for a solenoid, this is a solenoid, looks a solenoid, correct? And inside, when we have current through this solenoid, we can use a battery or we can use a generator, correct? We have a magnetic field inside, right? The magnetic field is produced inside. And this magnetic field is equals to, for a solenoid, is equals to mu naught, numbers of turns, divided by L, the length from here to here is L, right? The length of the solenoid times the current. Also, this quantity is represented by little n times the current. With this little n is equals to the numbers of turns per length. Okay, perfect. This is for a solenoid, inside of the solenoid. Okay, great. Let's go back then to this analysis. And what do we have? This is equals to negative n times the change of the magnetic flux. Remember, change of magnetic flux is equals to, this is for the previous chapters, this is equals to VA cosine theta. Okay, great. Now this is equals to B A cosine theta. Okay, in this case, the area, cross-sectional area right here, this area is constant. The numbers of turns is constant, right? The angle is gonna be perpendicular, right? The angle between the magnetic field, this is the magnetic field, this is the area, is gonna be perpendicular. So, well, perpendicular, but the direction of the area, remember, it goes in this direction and this is the direction of the magnetic field. So the angle is 0, cosine 0 is gonna be 1. Okay, great. So this is equals then to just n area change with respect to time of v respect to time. Correct? Perfect. And then this is equals to what? When we apply this analysis, what do we have? This quantity. Well, let's introduce this value, and this equals to negative NA times what? This is a constant, stays the same. Another constant, correct? What else? I'm right here, okay? Divided by L times, well, now it's gonna be the change of the current respect to time. Okay, times the change of the current respect to time, because the current is changing for this EMF. Okay, perfect. And then this is equals to negative n squared a. What else? Mu naught over L, again changing current respect to time. And now let's apply this condition, right? And it's equals to little n, big M, right, divided by L. When we are doing this, this is equals to, it's gonna be equals to mu naught. It's gonna be equals to mu naught n squared L times the area. Correct? Times the area. Times what? Times changing current, of course, respect to time. Correct? And that's gonna be the electromagnetic force. Now, when we compare this one more time to this part, what do we have? we have that the electromotive force, this is only the magnitude, is equals to what, L? But what should be now L from here? What should be L? L is equals to, this is the self-inductance. When we compare this to this, it's gonna be equals to mu naught n squared L times the area. This is for the solenoid, okay? For the solenoid, the inductance is equals to mu naught is inside the solenoid, n squared L times the area. Correct? Perfect. Now, let's go to the next topic, which is the energy stored in a magnetic field, or the energy stored in a solenoid, right? Which is with a magnetic field inside. Okay, let's do it. Let's do it. Let's do it. So we have that the electromotive force. The electromotive force, one more time, is equals to, in a solenoid, right, is equals to L, right, times, right, change in current respect to time, right? It's gonna be this one right here. Perfect. Now, but the current again is changing. It goes from 0 to a maximum. It goes from 0 to a maximum. In this case, what do we have? We have that this is equals to, again, current at the beginning is 0, and at the end is the maximum. Okay. And then what do we have? Well, what should be this change in current respect to time is gonna be what? Remember, change is final minus initial, correct? Okay, so this is gonna be L, the inductance, times L times current, the final current, minus 0 divided by the time, respect to time. Correct? And what is this? This is equals to inductance times current respect to time. Okay, perfect. But look, when we're dealing with energy, we relate energy to power. How do we define power? Is energy per unit time. Remember from previous chapters, power is energy or work, right? Energy and energy per time. Okay, now let's see what is the energy in this case. Energy is gonna be power times the time. But what happens to the power? The power in this case is gonna be the average because the current is changing, correct? So what do we have then? The average power is equals to the average current times voltage. Remember, that's the definition for power, current times voltage. But what should be the average current? The average current is just this maximum current, this one divided by 2. Maximum current divided by 2 times the voltage. That's the average power. Okay, great. But we can use also, because we're dealing with electromotive force. This is energy, be careful, this is energy. This is electromotive force. Also, we can represent this in this way, current divided by 2 times this electromotive force. Correct? Perfect. Now let's look for energy. Let's compare this to this is power from electric circuit. Now let's go to general definition for power, right? Power is equals to energy divided by the time. Okay, we can use delta T right here. Perfect. Now what is energy then? Energy is equals to power times delta T. So we are dealing with the average, right? Average power. Okay, great. Then what is the average power? One more time, is gonna be current divided by 2 times the electromotive force. Okay, let's do it. So let's substitute the value right here, and what do we have? We have the energy is equals to average power, current, right, divided by 2, correct, times this electromotive force, correct, times the time, correct, times delta t. Got it? But what is electromotive force? It's gonna be this value. So this is equals to current divided by 2 times what? Times this inductance times current, correct, divided by delta t. This is delta t right here. And then divide times, I forgot this one, times t right here, okay? Times delta t, okay? This is divided by delta t times delta t, this one right here. So delta t is cancelled. And what do we have? Energy inside of a solenoid is equals to the inductance current squared divided by 2. Correct? Perfect. Okay. Also, we can go back right to the energy and go and use this inductance. Let's do it. So if energy, let's use this U for energy. Energy is equals to inductance current squared divided by 2, but the inductance for a solenoid is equals to mu naught n squared L A, right, divided by 2. Okay, perfect. Times the current square, right here, right? Current square. Okay, perfect. But also, look, the magnetic field is equals to mu n current. If we take the square right here, right, it's gonna be square and a square, right? But look, we have already right here n square, I square, but this is what? This is mu naught square. If we multiply by mu naught, right, it's gonna be mu naught square. We have to divide it by mu naught, correct? And now what do we have? This times this is gonna be b square, right, divided by the rest. Okay, let's do it. So from here, this energy is equals to what is left. Well, let's start with this. One's gonna be b squared times L area divided by 2 mu naught. Okay, but look, this is the area, right, of the solenoid. This is the length of a solenoid. What is this product? This product is volume, right? This product is volume. So also we can arrange this in this way. This part, we can go to energy per unit volume is equals to v squared over 2 mu naught. And this is called the energy density. Energy density or energy per unit volume, right, is equals to energy divided by volume is equals to v squared, the magnetic field, squared divided by 2 mu naught, right? Okay, and we can represent this in this way too for the magnetic field, just to make it better. It's equals to, this is the energy density, is equals to v squared divided by 2 mu naught. Okay, perfect. Now let's go to transformers. That's the last topic for this chapter, transformers. Let's do it. Let's go to transformers. A transformer is a device for increasing or decreasing AC voltage. Transformer, okay, device, right? Device that increases or decreases AC voltage. For increasing or decreasing AC AC voltage. That's gonna be the transformer. Okay, and this is the picture for a transformer. We have this core. This is a iron core usually. This is used to concentrate the magnetic field. And then we have a coil right here, coil, correct, coil. This is called the coil that is connected to the generator is called the primary coil, right? This is a primary coil, and this is the numbers of turns, right, in the primary coil, okay? Primary coil. Okay, and this is the primary voltage, correct? Now we have a AC current that oscillate, and when we have, every time we have a change in the charge, when the charge accelerates, the acceleration of this charge, electric charge, produces a magnetic field. This magnetic field is changing. So it's concentrated through this iron core, and it goes to another set of coils in the other side, right? These are the secondary coil, right? Secondary coil. Perfect. And this connected again to a circuit. And this is the numbers of turns in the secondary coil, and we have the secondary voltage. Okay, and this is a transformer. We have two types of transformers. We have the step-up transformer, step-up, and step-down. The step-down transformers. The step-up, of course, increases the voltage. And how that is happening? Well, when NS, the numbers of turns in the secondary coil, is much larger, right, than the numbers of turns in the primary coil. And this is the opposite, right? That happens when the numbers of turns in the primary, correct, is larger than the numbers of turns in the secondary. Again, we use this to increase or decrease voltage. Right? For example, we're familiar to these high voltage power lines that we have sometimes on the streets. It says danger, right? High voltage could be 100,000, 200,000 volts. How that's possible? Well, using a transformer. But in our house, we don't need this high voltage. We have to reduce the voltage, and in that case we use a step-down transformer, right, to get 110 volts. That is the voltage in our house. Perfect. Now let's find an equation that helps us to work with voltage. In this case, let's use one more time the Faraday's law, right? The Faraday's law. In this case, we expect to have the change in the magnetic field or the magnetic flux, right, on the primary to be the same in the change on the magnetic flux in the secondary coil. That's the condition in this case. Okay, this change right respect to time in the primary is equals to this change respect to time in the secondary coil. When that happens, and we use the Faraday's law, right, we create this equation, this formula. It's gonna be again the electromotive force is equals to negative NS, right? What else? NS. This is NS. We can use this is electromotive force, right, for the primary coil. Exactly times what? Change in this magnetic flux. The same thing happens to the primary. Also, we can use voltage. Surely we use voltage, right? Voltage. Okay, and this is equals to negative primary numbers of turns in the primary coil, right? Times this change in the magnetic flux. But because these two are the same, respectively, that, right, what do we have when we divide these two? When we divide these two, we have that Vs over Vp is equals to Ns over Mp. And this is one relation, right, for one relationship for the transformers. Or we can use the equation we have Vp over Vs is equals to Mp over Ns. This is for transformers. Also, we can use conservation of energy. Imagine that this energy then is conserved, right? When the energy is conserved, we use also power. Remember, energy related to power. How do we define power? Power is equals to current times voltage. This is for electric conditions. But in general, power's definition is energy per time. Right? The energy is conserved, but the same energy right here, same energy right here. Well, we also can use power. Perfect. So in this case, we can say that power at the primary coil, right, is equals to power at the secondary coil. Means what? Means that current, right, times voltage is equals to current, right, times voltage, right there. Now let's arrange something like in this case, or like in this case, correct? We can have current from the secondary, right, divided by current from the primary is equals to voltage primary, right, voltage secondary, which is the same as this one, right? So this equals also to current secondary coil divided by current on the primary coil. Okay, and this is the main equation that we use for transformers, right, to increase or decrease an AC voltage. This is work only for AC. It doesn't work for DC current or voltage. Okay, great. Perfect. And with this analysis, we finish this chapter. Yes. Okay. See you in the next one.